Assalamu alaikum. Welcome to the course of Electric Machine 2, lecture number 9. Today we are going to study synchronous motor. First, let us remind and repeat what is electric motor. An electric motor is a machine which converts electrical energy into mechanical energy, and its principle is that when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force. So we all know what is motor. Simply it's convert mechanical energy into electrical energy, and when a current carrying conductor is placed in a magnetic field, it's experience a force. That is the basic principle of electric motor. Now, what is synchronous motor? So we study DC generators and DC motors. So a DC generator can be run as a DC motor in a similar way. An alternator may be operated as a motor by connecting its armature winding to a three-phase supply. So it is then called a synchronous motor. As the name implies, a synchronous motor run at a synchronous speed. Most synchronous motors are rated between 150 kilowatt and to 15 megawatt and run at a speed ranging from 150 to 1800 rpm. There are a few characteristic feature of synchronous motors. It run either at a synchronous speed or not at all. That is, while running it maintain a constant speed. As its name implies, it is a synchronous motor, so it run and it must be run at a synchronous speed or not at all. So it is not inherently self-starting. It has to be run up to synchronous or near synchronous speed by some mean before it can be synchronized to the supply. We will study this in the coming slide, so you will understand the concept of how it is starting. It is capable of being operated under a wide range of power factor, both lagging and leading. Hence it can be used for power correction purposes. So synchronous motor run at a synchronous speed, and it is not self-starting, and it is used for power correction purposes. Now let's see its construction. As in many machine we studies two basic or two main part. It have a stator and a rotor. So in a synchronous motor we have a stator which houses a three-phase winding in the slots of the stator core and receive power from a three-phase supply, and a rotor that has a set of poles excited by DC to form alternate N and S pole. The exciting coils are connected in series to two slip ring, and DC is fed into the winding from an external exciter mounted on the rotor shaft. So the two basic part or main part: a stator which we given a three-phase supply, and there is a three-phase winding in it, and a rotor that is excited through a DC source, and that is mounted on a shaft. So principle of operation, how it operate a synchronous motor. So for it we need to understand the diagram given in the figure. That is, we have a stator and a rotor. Initially, when the stator poles, that is NS and SS, and the rotor pole are denoted from north and south. So when a three-phase winding is fed by a three-phase supply, the magnetic flux of constant magnitude but rotating at a synchronous speed is produced. So when we fed a three-phase winding with a three-phase supply, a magnetic flux is produced that is rotating at nature, and it has some speed. So we are considering a two-pole stator that is marked with NS and SS, rotating at a synchronous speed, say in clockwise direction, with the rotor position is shown in this figure, this one, the first figure from left side. So actually when we have a stator marked with north and south pole, it is the three-phase supply due to which a constant rotating magnetic flux produced, so it is rotating. Suppose the stator pole are at the instant situated at point A and B. The two similar poles will repel each other. As a result, the rotor tends to rotate in anti-clockwise direction. So in this figure, when at this instant, suppose that a stator is in this position, that is, it has the NS and SS poles, and when we give a supply, it produces a rotating magnetic flux. So at this instant, when a rotor is at this position, so north and north pole repel each other and south and south pole repel each other. So for this way, rotor tend to rotate in anti-clockwise direction further, but after a half period, as we know, we providing alternating voltage, alternating supply to the stator. So after a half period, the stator pole change its position. So but after a half period later, interchange its position. In this condition, NS attract S and SS attract N, hence rotor tend to rotate clockwise, which is just the reverse of the first directions. Hence we find that due to the continuous and rapid rotation of stator pole, the rotor is subjected to a torque which is rapidly reversing. The rotor cannot instantaneously respond to such a quickly reversing torque. As a result, rotor remains stationary, and that's why a synchronous motor is not a self-starting. So now consider the condition: the stator and rotor pole are attracting each other. It is possible when the rotor pole also shift their position along with the stator pole, then they will continuously experience a unidirectional torque. So basically in this figure we can summarize what we studied, that we have a two-pole machine, that is, when we supply the stator a three-phase supply, it produces a rotating magnetic field. Suppose at that instant we have its pole NS and SS in this direction, and the rotor pole in the rotor pole north and south in this direction, and it is in the anti-clockwise direction. So at this position, both same poles they repel each other, so that's why it is in the direction of anti-clockwise direction. Another instant, when the stator pole change its position, now at A we have S and at B we have N. So at this instant, the north and S pole will try to attract each other, so it will in the direction of clockwise direction, so they have opposite direction. So in order to start it, we need a mechanism, we need an excitation to the rotor. So method of starting: the rotor, which is as yet unexcited, is speeded up to near synchronous speed by some arrangement and then excited by the DC source. The moment this synchronously rotating rotor is excited, it is magnetically locked with the stator and both run synchronously in the same direction. It is because of this interlocking of stator and rotor pole that the motor has either to run synchronously or not at all. The synchronous speed is given by the relation ns. The speed of synchronous is equal to 120 f, the frequency, by number of poles. So we need the rotor to speed up to synchronous or near synchronous speed by some arrangement and then excite it with a DC source. So after it is magnetically locked with the stator and both run at a synchronous speed in the same direction. It is due to interlocking of stator and rotor pole that the motor has either to run synchronously or not at all. Motor on load with constant excitation. What happened when we connected load to the synchronous motor? As we know, in a synchronous machine, a back EMF EB is set up in the armature stator by the rotor flux, which oppose the applied voltage V. This back EMF depends on rotor excitation. The net voltage in armature stator is the vector difference of V and back EMF. Armature current is obtained by dividing this vector difference of voltage by armature impedance. As we know, we supply three-phase supply to the stator, and excitation or DC excitation to rotor. So rotor produce flux and it cut the stator. In this way, EMF induced or back EMF induced in the stator, which oppose the applied voltage. So this back EMF depend on the rotor excitation, and the net voltage in the armature stator is the vector difference of the supply voltage and the back EMF. And armature current is also equal to the vector difference of voltage by armature impedance. So when we connect a load, there is a back EMF in the stator. Thank you for today's lecture.